Thank you very much, Vin, for the very kind introduction. Before I begin, let me ask, how many of you are students? Alright. If you are not students, then by definition you are professors, right? Alright, good. I wanted to know because maybe I can keep that in mind when I talk. Because the rumor is that students follow leaders very fast. So a lot of students have to talk fast. Okay, now, would you rather build this part too bright? Yeah, because if you cannot see this properly, please ask someone to cut out all the
That's fine, either way.
Okay, let me get started at the meantime. Okay, here is the title has been announced. Okay. Alright. So I will begin very briefly to tell you what coprime arrays are and what coprime co-arrays are. And I'll explain how to realize coprime co-arrays, either active or passive scenario. Alright. I will talk a little bit about beamforming with DFT filter banks in the context of coprime arrays. And time permits, I will talk about time domain coprime sampling and so forth. In fact, I will begin by talking about time domain coprime sampling and then go back to space time. If at all there is time, I will talk about the multidimensional versions and so forth. Okay. Alright. So, getting down to real details here. So here is a simple sample version of a signal, okay? Alright. So you can assume, for example, these are sample and values. Right? If you like, you don't need to do that, but if you like, you can assume these are a sample. Right? Just taking from the sample version. Okay. And now, imagine this signal is now sampled by two sets of samplers separately, two parallel channels of samplers at some arbitrarily smaller rate. They're smaller compared to the top rate. Now you realize that this pointer is not good enough to reach. Alright. So I'm going to use pointer here. Okay. So these sampling rates are much smaller compared to that. This is n times smaller, n times smaller. Okay. So imagine there is this extremely sparsely sampled set. The question is, are these two sets of samples any good for predicting anything about the signal at all? Initially it seems as if it's useless because they have sampled at a much smaller rate, arbitrarily smaller rate. If m is arbitrarily large, n is arbitrarily large, then it's very sparsely sampled, right? Okay. So for example, m could be 5, m could be 8, okay, some or any other section. So there is obviously lots of information when you go from there. Unless the signal is extremely bandwidth, this would contain lots of information and so forth, right? And so question is, can we do anything with all these? I will show that we can do quite a bit of useful things even with this set of samples. You cannot do everything with it. For example, you cannot in principle, you cannot in particular reconstruct that original signal. That would obviously violate channel sampling. So that's not what I'm after. That is not possible. Okay. And okay, some notations. You see this thing that for x of n, I'm going to denote that signal with x of n. Okay. This subscript C was meant to say continuous time. So that those are samples of continuous time signal. Okay. So there are few discrete notations of x of n. Yes. According to that notation, we have x m n and x m n. So these are okay. So look at this x m n, x m n. These are all estimated terms of x. Okay. So what I have therefore is this kind of a picture. Those are few familiar notations, right? Imagine there is this sample version x of n. This x of n is that sample version. Okay. And these are decimated by n, decimated by n. Those are the decimated versions. Okay. So the question now is, can we get any useful information about this signal from those decimated versions? Okay. What is obvious is that we cannot get back that signal because there is lots of information. But is there any other useful information we can get back? That's the question. Okay. I'll at least some useful things that you can reconstruct. Surprisingly, you could reconstruct a spectrum from UVC. Okay. So, slightly different notation is used here. What's going on here is that I am basically showing the same thing. These are the original continuous signal, sample m times smaller and n times smaller than some basic rate like okay. So those are the samples I am repeating. A lot of things here are repetitions. Okay. Those are the notations I used, and this is basically the picture that you get. Okay. The claim is this first claim. In fact, this claim will last for the talk. If M and N are Coprime integers. What is M and what is N? M is this number, N is this number. M is the extent of sparse sampling there. N is the extent of sparse sampling. Okay. Compared to the original sample. Okay. If these two integers M and N are Coprime, that means we have no common factors. 3 and 5 are Coprime. Okay. So 12 is not prime, but 12 and 30 are Coprime, right? So if these two integers are Coprime, then indeed I can get a lot of information about that signal. That's what I would find. Alright. Broadly speaking, that's what I would find. Now, for example, we can recover the autocorrelation of the original signal. Assume the original signal is wise and stationary, for example, that is totally wise and stationary. Then the autocorrelation of this signal at the original time, mind you, see, T is the original sample spacing. For example, the native sample spacing. At that spacing, I can recover the autocorrelation from these two signals. Even though these two are arbitrarily sparse, okay? This signal could be 10 times sparse at the desired sample. That would be 11 times sparse, for example. But with S1 and 11 Coprime, we can indeed calculate all these. That's one example. And in fact, all the examples and applications I'm going to show you at least today, well, at least, let's say 50%, are based on this fact that autocorrelation can be used. Okay. That's fact. I'll talk a little bit about why this is the case and then tell you the applications. But I also want to add at this point that this idea itself that we can reconcile the autocorrelation is not new. In the sense that people in array processing who talk about co-array, the so-called co-array concept, already know this in a slightly different way. They did not put it in this way, but this fact is basically there. So I am not claiming this as something new, but it has not been used. Surprisingly, it has been heavily underused. The fact that we can reconcile this. Yeah, I said we will see because I have not shown this. We will see. Now, for those of you, right, who don't recall, this is what autocorrelation means. Okay, it's an expectation where you have samples and samples here. Okay, so this is in particular this is the autocorrelation of a sample from the first sequence and the second sequence. Okay, so you can call it cross correlation, but autocorrelation between those two samples. Okay, so and if it's a stationary process, then this difference is really what matters. RK there. K is this difference really. Okay, so the claim is that as I claimed earlier, the autocorrelation can be calculated in all integer values, K, right? That has to do with the fact that M and N are Coprime, okay? And it comes from the following very simple result that you can see. Yeah, let's look at this thing. So what's going on here is the following. M and N are very simple, very simple result. This is the fundamental behind all the discussion. Okay? If these two integers are Coprime, alright, then you can always find an integer n1 and an integer n2. So that this difference can be any integer you want. Very simple theorem from Euclid's theorem. Okay. Euclid wrote those different volume physics in one of those problems. Okay. Several hundred years before Christ. Okay. But very well known fact that if m and n don't have common factors, then there exist n1 and n2 integers such that any integer k can be measured. Therefore, if this autocorrelation depends only on the difference between the arguments, which is the case for any stationary process, then the autocorrelation can be calculated in all integer values just by computing this correlation. This is the basic idea. Therefore, if we have samples of this for all times, okay, MT, 2 MT, 3 MT, all samples, and all those samples, then we can do that autocorrelation. That's the basic idea. Okay. This idea has been used, as I said, in array processing to compute so-called co-array. The co-array, as they call in array processing, is nothing but the set of all differences you can achieve. See this difference here. The set of all differences you can achieve is called a co-array of two arrays. If you have two arrays with spatial spacing or temporal spacing, set of all differences between the times or spaces you can achieve is called a co-array. Okay. Therefore, all I am saying is that the co-array is by definition the set of labs at which the autocorrelation can be calculated by definition. Alright. Okay. So that's the basic idea. Now, here what I have is basically I am just giving some kind of boring details how to calculate this. That's not a big deal. If we have samples for a long period of time like this, this is n, this is n, right? What you see is that because M and N are Coprime, the first time the samples overlap is here. N and G and N. That's the first consider the samples from where overlap samples are less than 0, right? So that can be regarded as one cycle, and then after that the pattern repeats. So what it is, you wait for this kind of one cycle, and then calculate the product of samples from here, and average them over several cycles. This is all you have to do to calculate. You simply regard this as one cycle. For example, take the product of that sample with this sample. Okay, mg and then 3mg, right? That difference will also appear in the next cycle, and so forth. Simply analyze. To do it over the cycles, there is a latency of the cycles in this calculation. So it's simple. Okay. Now, so like I said, the set of differences that can be calculated. Okay. Suppose you take only one cycle like this. Okay. This is one cycle. In one cycle, the set of all differences you calculate is called the so-called co-array of these two arrays within one period. And there are so-called modes in the array in the sense that even though, okay, the idea is this, even though all integer values of k can be generated according to Euclid's theorem, that is true only if n1 and n2 are allowed to be any possible integers. If n1 and n2 are in finite ranges like this, and the finite ranges like that, then k will have a set of distinct values here. It will have m distinct values. There is a very simple figure, very elementary figure that says if m and n are coprime, then in that range k will have m distinct values. But because that range itself has almost 2 times m values, there are holes in that range, people say. So k does not take necessarily consecutive values, but it takes values. So holes basically means it's not a consecutive. So to show you an example now, before proceeding with more applications and so forth. Okay. Imagine there are these n elements here at the top, and elements, locations, multiples of m. So m in this case is 4 and is 3. Okay. So these are the two sets of elements. You can think of this as time or space. In space they put hand arrays like that, and then they create the so-called co-array to do all sorts of things. For example, DOA estimation and so forth. Okay. So you can think of this as space or time, your preference. Okay. All right. So suppose you have these two arrays, you calculate the set of all differences you can get from here. Okay. Here is the set of all differences. So this is what I mean by holes in the co-array. Because see, there is a gap here, there's a gap there. That's it. Okay. And there are holes there. And this is so-called symmetric difference. What I mean by that, you took this difference, you could also take the other difference, the negative of this side. This minus that you can take, right? If you do that and take union of both, then you get a bigger set. Not 2 times bigger because there is overlap, but you get a bigger set. That set is the useful set. So what is the physical meaning of this again? The physical meaning is this. Imagine this is spatial, instead of temporal or anything, it's spatial, okay? Sense of uniform linear array. Uniform linear. There are 2 dual arrays here, right? If the spatially white and stationary signal is impinging on these 2 arrays, then the order correlation of that signal can be calculated at all those arrays. So this is the fun. If you understand this question, everything else is simply repetition of this camouflage in this form, camouflage in this form. Okay. The basic idea that I'm repeating, taking the time to speak, namely, if you have a spatially wide sense spatial signal, okay, just again, temporally, wide sense spatial signal, right? And then it's falling on this array, okay. These 2 locations are the same. In fact, we need only one sensor for those, okay? You don't need to have 2 sensors, they are the same. If it's coming in like that, then what are the spatial lags at which I can calculate the autocorrelation? The answer is, these are the spatial lags at which I can calculate the autocorrelation. So I can calculate autocorrelation at many more points than the number of sensors. 3 plus 4, 7 sensors, right? That is almost how many? 18, 7, 16, I think. 17. There are 17 of these green dots here. 17 places where you can calculate. Okay, so that's the fact number 1. Fact number 2, what is the impact of this? Okay, one example of an application is for people who are familiar with array processing, which I'm sure many of you, professors especially, familiar with array processing. Namely, supposing I have an array like this with 3 elements. Array with 3 elements. I can identify sources, 2 sources with 3 elements. And if I had an array with 7 elements, see this has 3, this has 4, I don't know how many. 3 plus 4, 7, right? 7 physical elements. With 7 physical elements, I can identify up to 6 sources. That's what I know. So that's the number of degrees of freedom, let's say. Okay, if I have 2 sensors, I can identify 1 source in space, location. Okay. So the number typically you can identify is n minus 1, where n is the total number of sensors. Okay. Now it turns out that the sensor identification algorithms, music and all that classic algorithms from for 30-40 years, like those algorithms depend only on autocorrelation. You found an autocorrelation matrix and there is something called a noise subspace, you put it in the denominator. There's a big details about how you compute the spatial locations of targets. Okay. And it all depends only on autocorrelation. Now the co-array here, the different set, is the set of labs at which the autocorrelation can be calculated. And for example, you have the music algorithm. Just to take an example, music is okay. That algorithm can identify how many sources in space. The answer is the number of sources that can be identified is the number of places where you can calculate autocorrelation minus 1. In this case, I think this is 17. 17 those little dots. 17 minus 1 is 16. So I can actually identify 16 sources instead of how many are there? 3 plus 4 is 7, right? If I directly use those two things, directly use 7 sensors here and here, I can identify only 6 sources. Whereas if I go here, I can identify 16 sources. This is the impact of knowing that the difference set is a much larger set with 2 coprime arrays. The arrays were in coprime, for example, two arrays like this, located exactly same. This element is located here, this element is located here, and so forth. Then, okay, then you don't get as many, as large a co-arrays. Okay, the idea is, suppose you have 2 arrays, length and length. Okay, n sensors. If you don't place them uniformly, then the co-array has only size n plus n. N plus n. So it's linear. That means the number of sources you identify is linear in n and n. Linear in n plus n. Whereas if I do this, put them in coprime locations, then I get order of n degrees of freedom. Meaning I identify order of mn sources instead of order of m plus n sources. That's a fundamental idea. It's the same idea that repeats over and over and over again. So that is this is a very crucial idea. Okay. So again, if I have m plus n sensors, then I can identify about m plus n sources if I use it conventionally. Whereas if I put them in coprime locations, then I create a co-array that is order of m times n larger, and therefore I can identify order of m times n sources. That's a fundamental idea. This idea came from a previous paper I wrote with my student, so-called nested array idea, which I will mention later. And this idea was inspired by the previous paper. Okay, that will come later. I'm sure you know exactly what I'm saying about nested array, but there is a view, there is a separate slide of that. Okay. But so this is basically saying the same thing. Okay. Those locations I'm just putting numbers there. So it's not much important what that difference. Okay. The main point is that there are 17 differences there. There's a hole here which is a slight problem. Hole meaning there's a missing co-array location here, which makes the algorithm slightly more complex. But later on, I'll come back and patch up the hole. Okay. But okay, like I said a few times before, I'm actually formulating different squares. Different sets have been known as different squares in the array processing. This idea has been there, but the only difference is look, co-arrays have been there for a long time in array processing. Salim Qasim, for example, many years ago wrote a paper. And co-prime concept has obviously been there since Euclid. Okay, 2300 years ago. Yeah, something like that. But surprisingly, co-prime co-arrays nobody has bothered so far to consider. Okay, co-prime, then the co-array has order of m and n. So 2 arrays, approximately n sensors, you can get approximately order of n square sensors. That's okay. So basically, we are combining 2 things that are known. And surprisingly, it opens up a lot of good things. Alright, good. That's it. Now, just very simple, not exactly theorem, but still it's very useful fact. Namely, you know how there are holes, right? I'll show you how to get a continuous patch of m and co-array locations, and then we will go on. Okay. So bear with me for some amount of detail. Okay. I cannot give too much detail towards the end of the talk, but I think I'm still fresh from my coffee, so little detail. Okay. So what I'm saying is that now, imagine there are 2n plus n measurements, meaning 2n plus n sensors. You know how we have n sensors and m sensors? Now we have 2n sensors and m sensors. Okay. Right. So the first one has 2n samples. This would be samples to the time domain or they samples to the spatial. These are n samples. Okay. This has only n samples. So the total number of samples is not n plus n, but 2n. So what you do is you have some redundancy in the number of sensors for one number, not the other. Okay. If you do that, if you pay that little price, then you can generate a beautiful continuous range of m times n without holes correlations. Okay, that would be it. Okay, for example, we have this. Right? So the difference now is that instead of starting at m, okay, this one has 2n. Not to create this as absolutely n. Okay, that's it. Okay, so if you have this extra thing, okay, then you get a continuous stretch of m and correlations or m and difference relations. Okay, like this. See now. So the autocorrelation in principle. So the idea is summarize it slightly differently. Okay, more pictorially, or engineering very simple. And given the samples from 0, okay, these are spaced by m times larger in terms of there are n, instead of n samples, there are 2n samples. Well, 2n or something. Okay. And similarly, instead of m samples, there are 2m samples. Okay. If you have this, then you look at all the possible differences. Okay, those differences will have a continuous stretch without holes of those autocorrelations. That's extremely useful if you are doing music with m and autocorrelation. Just give an example. If music is your favorite algorithm, you can do that for m and sources, m and minus some sources. Okay. And of course, you do get other lags beyond this, but those are not for this particular slide. Okay. So here's an example. What I'm doing now is, this is all repetition of the previous example. Okay, nothing new here now. I'm reproducing the example where the active and 4 sensors respectively. That's what this is. Okay, and if you have 2n elements instead of n elements, okay, then exactly the only difference is that this has more sensors. That's what we mean. Okay, what can I say before? If you do that, you get this beautiful continuous stretch. In this particular example, that's the difference. But if you take the symmetric difference, which also includes the negativeness, then you get a really beautiful continuous stretch. So the main point therefore is this. How many is that total? 1, 2, 3, 4, 6 plus 4 is 10, right? There are 10 sensors. If I use these 10 sensors in the conventional way, I can identify 9 sources in space. Whereas if I use this, I can identify, see that number of sources. It starts from 14 to minus 14, how many do you have? That's 28, 29, right? 29 minus 28 sources. So instead of directly working with the sensors, I work with this symmetric difference set that opens up different freedom to identify sources. That's one of the simplest advantages. And all the advantages I am going to mention are simply variations of the same thing. Okay, good. Now let me ask you something. Are the lights okay? Do you want these lights to be? Yeah.
Number 2 here, the minimum number of elements required to fill the hole?
Like this, yes.
There is a minimum.
Fill the hole to get this continuous patch of red, right? Because outside that there are holes. You see that hole? It is still not entirely hole free, but in order to get that patch of red M1, that is a minimum. If you ask me, is that a theorem? I don't think so. So the point is this: with 2n there, right? The result is that you will get a continuous patch. Without 2n, will you ever get a continuous? Is there an example like that? I don't know actually. Actually, it's a good question. Converse, I don't know. I can't think of it, but I would rather think of it after the talk. Yes. No, in one direction it's a theorem. The other direction, there is no theorem yet. That's because I am not talking about it. Thank you. Good. Now, returning again to this idea. Let me see what is new here. Okay. This is something I already mentioned, so let me do it here. Okay. So what's going on here is that imagine it's a time domain signal time domain, right? That's the autocorrelation you want to calculate. Like I said, we take products of signals, for example, that signal and this signal, take the product, that's this, okay? And then you simply, to calculate the average, you simply do this. See what happened, if you look at the second term here, this term here, n times ML, n times ML, right? That is basically the ML, that's like shifting the whole thing by an entire period, right? So this is the kind of physical average that you use it for a time domain signal rather than a space signal. This is exactly the formula you use for doing the averaging to calculate the autocorrelation. The signal is sufficiently stationary over a long period of time. And remember, the beauty is that this n and m can be arbitrarily large, so no matter how sparsely these two are, you can still calculate. autocorrelation at that final resolution. Space R. So that is one fundamental idea we have to take on this. Good. Now, therefore, the average sampling rate. So the sampling, as far as autocorrelation is concerned, we have successfully sampled autocorrelation at the rate 1 over T. 1 over T is the sampling rate. Whereas for these guys, sample rate is 1 over MT. 1 over MT, right? So the total average sampling rate is like this, but half. Well, not half, because we have both of them. It is this. And that can be made arbitrarily small. And that can be made arbitrarily large. You can make this go to 0 to 1. Still, you will get autocorrelation. And the price paid obviously is latency. Because the longer M is, more you have to wait to get the results, right? So if there is enough stationarity in the signal, you can do it, otherwise it won't be useful, obviously. So there is an obvious trade-off between latency and sampling. Right? The more you want to reduce sampling rate, the more you need. Very simple trade-off. Obvious, right? Good. Okay, so everything here has been said already. So price paid is sorry.
Can I ask you a question?
Yes, sir, please.
So you centered the discussion so far on this trade-off that you just mentioned, and also on just 2 coprime decimations. What if you did many more decimations?
Many more decimations will be useful, actually, to get higher order statistics. Instead of autocorrelation, if I want third moments and so forth, that's a useful way to go. Right? So that has been attempted in array processing with a different reason, but not with Coprime, basically. Okay, in that context, people have not done that. In a totally different context, Shia has tried the following. And this goal was to identify sinusoids in noisy processing problem, right? There we showed how we can identify sinusoids even after wiring time is spread. But he required many Coprime samplers, like he mentioned. He argued that, for example, he has an example where 2 sinusoids could be identified with 4 pairwise Coprime samplers, for example. But our claim is that you can identify any number of sinusoids, limited only by m and n, okay? Order of m times n sinusoids, with only 2 Coprime samplers. Therefore, if you do it this way, go to the covariant. In Shia's work, he did not go to the covariant domain, but we go to the covariant domain. We name the different sets. And to do so, you need only 2 sets of samplers to do that. With higher sets of samplers, the real advantage is that if you are interested in higher order statistics, you could calculate them by taking products of 3 things. But directly, this particular problem won't be improved by using more. That's the problem.
Filling holes by using multidimensional.
Filling holes can be done either by that, or it can be done directly by using more sensors for user. Because when you fill holes, you need to pay the price one way or the other. By using more redundant sensors, right? That's what that particular theorem I showed you is where you put exactly n more sensors and fill the holes to some extent, right? But no matter what you do, there will be always holes in the periphery. There will always be holes, order of n holes in the periphery. Yes, sir.
Can I ask you a question?
Absolutely.
If you know the distribution, you do the in-sample estimation of your correlation function, then they are all equally accurate. That's fine. But if you are doing experiment and you are going to use average to estimate the correlation, right? Then the accuracy rate here may not be completely perfect. Every point you may have very few to average. Is that correct?
That is true. So that's absolutely true. For example, if I have only, take that example, right? You know, take the sensor, right? There are n sensors with spacing m sensors with spacing n, right? If that is all you have, then the autocorrelation is estimated in one single snapshot. That's going to be very poor. That's going to be very poor. So if it's a spatial problem, where it's a spatial sensors, then we have to do snapshots in the time domain, and I do the average. More snapshots will work better. Whereas if it's a temporal problem, then you have to average over more periods in time. And how well it will work depends upon how many more freedoms we have for the averaging purpose. Absolutely. Yeah. Like any method, it depends on autocorrelation estimate, right? This method will suffer if there isn't enough statistical averaging. That's absolutely right. Absolutely. Any other questions? Yes, sir.
So it's crucial that the sampling periods are rational multiples, right?
Sampling, that's exactly what it is, right? That's exactly what it is. So the two sampling rates, if you take the ratio, then that is an irreducible number. M over n is irreducible. Because m and n are Coprime.
No, I'm asking what if they're irrational? The
Same
two
thing.
sampling ratios are irrational multiples.
Oh, if the sampling ratios are irrational, then what do we do? Then we cannot do this. But the point you have to remember is this. Here we choose how to sample. See, we put the sensors where we want, and we put the sample location where we want, right? So what I am saying is that you choose the sampling this way, then you will be able to produce a rich difference set. If you don't choose them this way, the difference set won't be so rich, meaning you won't have order of m n. That's right. So irrationally it won't work like this at all. You won't get a uniform content because the goal, what is the goal? The goal is to produce a different set that has order of m elements at number one. Number two, that's a contiguous set. That way, standard algorithms for direction finding and so forth work with contiguous set of order. Contiguous means without both set of order correlations. To produce that, this is one way to do it. The other way to do it is a so-called nested array. But then with irrational things, you don't produce such a uniform set. Something else will happen, some other. It may be interesting in its own way, but it won't be interesting for this kind of application. Right? Anything else? Good questions. Now, alright, so this is a very simple application again. Mind you, all the applications are classic, okay? But somehow it seems that it is not compared query and Coprime. So this is, when you read this system, it was very, very interesting. See? So, standard idea of identifying sinusoids and noise, right? Imagine we want to identify sinusoids and noise. Okay, now everything is in time. Okay, time and sinusoids, right? So again, this is sample spacing. That's original sample spacing. That's sample spacing right? The maximum identifiable frequency is like this. The t. Okay, omega. So pi over t is kind of like the Nyquist rate corresponding to this. Okay, so you can identify frequencies up to the Nyquist rate of that. Even though these were sampled way below Nyquist rate, sub-Nyquist sampling, sub-Nyquist sampling. If n is very large, this is sub-Nyquist. Still, because you can compute this at Nyquist rate, you can indeed identify frequencies up to that rate. So this is the basic. So someone you were asking, right? So this is the basic idea of how you can identify sinusoids, even though they are very sparsely sampled. Professor Shah from Delaware University, he had totally different method about 10 years ago, where he would use many different separates, a bank of samplers that are mutually Coprime. Because he did not go into the Coprime domain, the co-array domain, he had to use so many samplers to get the same. Okay. Alright. Now you ask me what is the technique. I will very, very briefly mention again. The idea is once you know the autocorrelation, there are any number of techniques you can pick up from textbooks, impact bars, textbooks, and so forth, right? To go from autocorrelation to identifying the sinusoid. That's just like the UOA identification problems. Okay. There are some differences which need to be worked out still. Some details that are not so obvious, but has to be worked on. Alright. So historically, like I already mentioned a few times, Coprime itself, well, Euclid is always a God, okay? Leaving God out, Euclid out, who else did Coprime? Okay? Coprime has been done in the range of 20 years ago easily for range improvement. Range is the distance to this target can be identified. That depends on the pulse rate. Okay? Pulse rate determines range. If you have two separate pulses at usually Coprime rates, you can dramatically improve that range. Okay? That has been very well known. Okay? Take up any standard radar book like Sparse. Okay? And estimation of multiple frequencies in sinusoids. This is the one that I was mentioning. Professor Shah, almost 10 minutes ago, probably yes. Those things are known. And like I said, it requires too many more samplers. And then this is much newer. Recently, meaning a month ago, I think not even a month ago, it's only coming out in October, so a month from now, right? There will be a paper, signal processing lecture, okay? Where we talk about system identification using Coprime pulse. Okay, that I think is very new. We were surprised also that we could do this. And that's a very theoretical kind of idea. I will describe to you next, okay? After that, depending upon time, I will go through that. So let me briefly mention, and other than that, okay, so like I said, Coprime has come up after Euclid many times in the history of signal processing, okay, 12. Well, not really that very many times, but 12 times, okay. And in multidimensional processing, those of you who do multidimensional processing, you know about decimators being coprime expanders, and decimator and expander. Coprime can interchange them, and there is multidimensional versions of like coprime matrices, community matrices, and so forth. All of that is a multidimensional process, of course. Right. And co-arrays, like I said, has been there for a long time. And there are things called minimum redundancy arrays that people use, where you use an array. Minimum redundancy basically, what it basically means, if you compute a different set, it's a very rich set. But the only problem is there is no systematic, mathematical, known way of putting the sensors to compute the minimum redundancy locations. So there are problems with this. Okay. Now, whether all these references are popping up. Those of you interested in papers, either email me or I will email papers to you and Professor you can follow that to you. So if you could kindly remind me, I'll send you a few papers. Alright. Now, let me totally different application for those of you who don't want to hear any more about interaction findings on those. Alright. So let me tell you about system identification. This is also old stuff, but it's a very new way to do it. Imagine there's an LTX, simple LTX, continuous. I want to identify this system. Not exactly the system, but samples. Continuous. How can I identify a very continuous sample, right? Continuous is uncountable infinite, which cannot be done. Right? Let us say we are interested in finding the samples. With some space in T, capital T, you choose in T, not necessarily something there, not necessarily language there. This is not a random system. Okay? You choose any T. T is 0.7. Now, to do that, what I do is a convention will you simply send an input signal at the same space, T. And you sample the output at the same spacing. Alright. Very simple. This LTI system could be a channel. Very simple linear time client. Right. Now, once you do these, you can, for example, that input could simply be an impulse. Okay. If that input is an impulse, then the output is of course the impulse response, right? You have sampled the impulse response and already found. So it's very trivial, right? So applying an impulse sampling output at that particular rate, you can trivially compute this. So it's a very trivial problem. But the point is, if you can do it other ways which are very interesting, you don't need, the point is this, you don't need to sample the output at that spacing. And you don't need to send the input at that spacing. You can sound the system out at a much smaller rate, you can sample the output at a much smaller rate and yet calculate all those samples. I'll show you. Okay. I won't show you now, I will show you what the basic theorem is, and you read the book in the paper. Okay. So, now, it is well known that if I have this exactly this picture, input and output this picture, any standard digital communication book, page 1, you will find the following. If you have that set of input and output sample like that, then the system is equivalent to a discrete time system. And the discrete time system impulse response is exactly this impulse. Okay. So first you have samples coming at the impulse train at the input and output is sampled. Effectively, the system is a discrete time system. Alright. And the impulse response is exactly the impulse response we want to know. Okay. And xn and yn are the input and output of this, right? So this is a standard decomposition. If you know the input x of n, you measure the output y of n. Well, in practice it is noise. There is no great story. We were correct to that. Okay. But given the input and the output, matter of decomposition, you may not do it. That's the point. This is standard decomposition. Okay. But the point is this, you don't need to do this. You can do much lower sampling. So let me explain that in the next slide. Okay. Okay. So like I said, this is the right? Now, that's the okay. Okay. So nothing new here, just literally the same figure so you can see it. Okay. What I do here is see the input, sparsely located sounds. I sound the system out, much more laid back, lazy, okay. N times larger space. N is arbitrarily large, 10,000, any okay. But, and then pulse at lower rate. Okay. I also sample at a much lower rate. M times. Not n times, that will be disaster. If I sample n times lower rate, that will be disaster. I am sampling it thoroughly so that this M is Coprime to this n. That's it. If n is 1000 and if n is 1001, they are both. Okay. Two consecutive integers are always coprime. Okay, 20 and 21 are coprime. 1001 are coprime. Right? So you choose your favorite integer. Okay. Sparsely sound out your system. And then choose any integer that's coprime. Smaller, bigger, any integer coprime. Right? Very sparsely sound. These should be sampled. Clearly, as long as the system doesn't change. See? From that set of samples and this set of samples, I can actually identify that set of samples as the original fine dense. Sparse pulsing, sparse sampling, usually coprime. I can identify dense. That's it. That's not so obvious. Okay. And I'll very briefly put up one slide of details and then you can read the paper for actually. Right? Okay. Yeah, all these are talking about after I said these things. So the answer is yes, as long as these are coprime. That's it. The answer is yes, we can reconstruct that set of samples. Okay. And like I said many times before, M and N could be arbitrarily found. That's it. Okay, so this is, I think. Oh yeah, here is the paper. Well, actually, even though it says October is a time you get a printed copy, okay? SP records these days come in packs of 3, the printed copy, 3 months, 4 months, but it's already there in Explorer if you're interested. If you can download it, just email me or email it to us. That's a very simple result actually, but let me briefly tell you about it. The reason I wanted to mention this very simple result. The coprimality, there are many different ways in which you can apply this coprime. This is one. And beamforming is another which I have not mentioned yet. I don't think I will have time to come to beamforming. With coprime, you can do very beautiful things in beamforming. If I have time, I will mention that. But very briefly, how this works is the following. Okay. You know how if I have a traditional channel, input is pulsed at a rate, output pulsed at the same rate. Then it becomes a deconvolution problem. Remember that? Deconvolution problem. Because it's a digital filter. Now, if these two are two different rates, that's a different rate. Right? Yeah, this is one, this is one. Right? Yeah. Then the discrete and equivalent is not anymore just an LTI system. This, but it is an LTI system with an expander. This can be shown. Mathematically, you can prove that if n is equal to 1 and m is equal to 1, that's just a traditional LTI system. Then it reduces to uniform sampling here and identical sampling here. Okay. Okay. Now with n and m this is what it is. So this is a multi-rate system. So called, what is this called? Fractional sampling rate alteration system is called. Okay. So problem of identifying those samples. Why is now? To identify that system sandwich between the experiment and the researcher. Identifying from what? From known input and known input. That's what it is. So it's not a simple deconvolution. This is very tricky compared to it. It's not even obvious that it can be done. But let's assure it cannot be done. If m and n had a common factor, I can prove that it cannot be done. It's provably not doable if m and n are not known, and it's provably doable if m and n are known. Why? This is the basis of it. Okay, it can be shown again. Sorry for this jump. It can be shown that this thing here is actually equivalent to my own system like this. Where h of c is a m input n output transfer function, where m and n are that m and that m. So like it's equal to my own LTI system with all these things. Basically, what this means is this. Okay. Those of you not familiar with this notation, basically this guy is said here is just one block of that. One block of m successive samples. This is one block of n successive samples. Okay. So you take this in blocks of m, take this in blocks of m. So there is an input sequence, vectors of size n such a sequence. Vectors of size n is a sequence. This vector of size m and the vector of size n, those two sequences are related by LTI. It can be shown that this LTI system can uniquely found. That's the point. Given that system, I can identify this unity. Given this, I can go back to the unity. So there is a 1-to-1 correspond. 1-to-1 correspond. The main point is that this identification is been reduced to a problem of ordinary micro deconvolution. That's it. If M and N are unity, which is conventional way of summing the just ordinary deconvolution. Now it is every bit as ordinary except it's a micro deconvolution because this is a micro deconvolution. So any technique to identify a MIMO channel from input-output measurement can be used. Alright. Again, sorry for not giving the proofs that would take more time on this, but please do read the papers again. Alright. Okay, I will go. Okay, so now in space, and now we turn to Coprime arrays in space again. Okay, how much time do they have? We have more like 5 minutes or 15 minutes?
We will have 5 to 10 minutes.
Okay, great. 10 minutes is great. That's fine. Then I won't go into the two-dimensional part. I have a separate file I have to open for 2 weeks. That will take another hour. So, yes. So wrapping up 1 dimension now. Okay, 1 dimension now. Space again. Now look, the spacing here is the times and the spacing is the times. And that's what is I will go with. So traditionally in array processing we know uniform linear arrays. The spacing between elements is lambda over 2 traditionally, or small. It's larger than that there is something called spatial, so-called gradient loads and so forth, all sorts of problems. So the things are usually spaced apart by lambda over 2. So now we are rarely spacing apart by n times aspects. That is like downsampling, sparse. Similarly, spacing apart by n. That is why the title of sparse arrays is sparse with respect to what? With respect to conventional way of spacing in array processing, which is just lambda over 2. Lambda being the way. Okay. Right. Now you take these things and as a M and N are cotimes of work. Okay. As I mentioned before, if they are coprime, okay, this is just an example. Okay. Yeah. As I mentioned before, this difference coarray has M and elements in the region, and you can get them to be successful. These are basically the few measures of what you have seen. So the point is that from M plus N distinct elements, you can get order of M and freedom, right? That's the basic idea. Now, this example already came up. And one thing I want to briefly mention, so-called nested array. I want to mention this because the idea for this Coprime Coprime coarrays came from this nested array paper, which was primarily authored by student, which also came out this year. Okay, this month, in fact, last month. Okay. I'll briefly mention what that is and how we. Okay. So I will skip this part again because this came up many times. Okay. Sorry for doing this real-time decimation, but I need to do this because I want to mention a little bit. Okay. Sorry about this. Okay. 2 things I wanted to mention, and then I'm happy. Okay. Give me like 6 minutes. Then. Okay. Now what's going on here? I will tell you something about the so-called nested array, which my students. Yeah, pause, she should get a lot of credit for this. But before that, something else totally else. So go back to Coprime. Okay, throw your mind back to Coprime again. Okay, what I have done is now spatial. In space, imagine there's an array here, M sensors, and so forth. Space apart, n times bigger, m times bigger, and then Coprime. Now I'm putting a DFT. Okay. So if I traditionally do this, I get several beams here, so-called beam space. I get M beams here and M beams here. Okay. Now. Traditionally, if I have an array with M plus N sensors, okay, M plus N, 10 for example, 10 sensors. If you have 10 sensors, then the beamforming, the beams, can have 10 distinct beams in space. Just like a DFT filter bank with DFT 10, right? You can have 10 beams. Okay. With 20 sensors, you can have 20 distinct beams. With M plus N sensors, traditionally you can have only M plus N distinct non-overlapping beams in space. So the beauty is that Coprime spacing, if you work in the coarray domain, you can get something beautiful. Then you can get M times N narrow beams. Beams are so narrow that space is divided into M times N non-overlapping slots, and you can get M times N beams by using M DFT and N DFT. So computationally it's fantastic. In terms of number of sensors, you don't need M N sensors, you need only M plus N sensors. How you do is, I will very briefly mention this, again all the details can be found in the paper, right? Basically what you do is take this, there is spacing N, right? That spacing N means the beams have this N over here, and the spacing M means beams have this spacing N. Okay. So if you think of this as a filter, this filter has many pass bands because of this N over here. This has many Passbands. But when you multiply these things, many Passbands kill each other and then you get very narrow Passbands. So, okay, very, very briefly, sorry for the brief here, but we have to learn now. Okay. So the first one, what you can generate is m beams, each beams will have one Passband. This has n beams, each will have one Passband. But when you multiply them, okay, we can generate mn beams, and all those beams will have very narrow bandwidths. So this is another thing you can achieve entirely in view of coprimality. So not only in time when you can calculate autocorrelation, the manifestation of that fact in the frequency is that with m plus n sensors, you can get order of m and beams that are not overlapping the frequency. Frequency means spatial angle. In time processing, frequency is actually translates to spatial angle. Okay, that's a very important idea. Okay. So again, I'm doing a little bit of real-time estimation. Close your eyes and tell you to open it. Okay. In fact, do the third piece, guys. I'm going to show you right away here. Okay. What's going on here is this. Okay. Now, here is those multiple beams generated from one particular array. Okay. And this is the other one, and these are DFT shifted versions. Okay. So I'm going to show you all the possible shifted versions you can get from this. Okay. So again, briefly, what's going on here is this. There are two arrays, M array and N array. That is one particular beam, and that beam unfortunately has multiple beams. Right? Those are the DFT shifted versions from DFT to that. Those are the DFT. Okay. So this is basically a shifted version of this DFT shift. That's a shifted version. Okay. So there are three shifted versions of this. Each of them has 4 columns. There are 4 shifted versions of each of them have 3 columns. But if you take anything from this table and multiply this with a different thing, for example, multiply this G with this H, you get only one non-overlapping column. Okay. So you take this and multiply this, you get only this non-overlapping column. So even though there are multiple beams in every one of those filters because of this sparse spacing, when you multiply them out, there is only one beam. So you can generate a total of 12 beams in this case, even though the number of sensors is 12 beams because 4 times 3 is 12. Okay. So any one of these, you can take this, multiply with any of these, you get 4 beams. Take this, multiply with any of these, you get 4 beams. So there is a total of 12 beams. Okay. So again, summarizing, even though the example is slightly better, summarizing the basic idea is that with M plus N sensors, with M DFT filter bank and N DFT filter bank, you can create the illusion as if there is an N times N DFT filter by going into 2 array. That's it. This is the fact. Okay, I'll show you an example. Now let me see if I can find an example. Very nice. Okay. Yeah, here is an example. That 6 and 5. Okay. 6 and 5 is 11. Conventionally, with 11 sensors, you can have 11 beams uniformly filling the space. Now we have 30 beams uniformly filling the space. Now the quality of the beam square, what we made, this beam is only about 5 billion attenuation. That's because you can do that. You can use the multiple science. You can improve the beams easily. Okay, that's not a big deal. You can get beams of better quality, but the main point is that from order of M plus N beams, you can get order of M. That's a fact. Just by doing both. Okay. Now, the fact is, we can go on for another hour, but it won't be fair to all of you. 6 o'clock. I'm standing in between dinner, so I think I will reluctantly stop here. Take questions.
Then you're looking for M1 and N2 compute the N1 and N2 analogs for those ranges. Of course, it's not a problem you're setting. Whereas in those settings, getting them explicitly is an interesting story by itself. But I'm curious if does it come to life and you go to the identification problem? The identification problem, where you advance from the ultimately you reveal the minor story.
Actually,
we have to resort to this.
this problem turns out to be not a major problem. First of all, you can either do Euclid, or in fact, you don't even need to do Euclid. If m and n are small, you can look at it very simple, right? Because in that case, m times n is the number of distinct k's when given for the table, right? And where it was actually more interesting for us is the multi-dimensional version. That's really a beautiful thing because m is a matrix of integer matrix. For example, 2-dimensional 2 by 2 integer matrix. N is a 2 by 2 integer matrix. And we have talked about these matrices being Coprime matrices. And similarly, there is m n1 minus n n2. Okay, if m and n are Coprime, then we talk about so-called left Coprime is what we really require in this problem because n1 is on the right of it. Right? Yeah, to identify n1 and n2 for a given k vector, no k is a vector. The same k is an integer vector. Identifying that k integer vector, mathematically it's the same problem because basically you are working in a domain where division theorem works. Division theorem basically says there is quotient and that theorem is still okay. Therefore you can still do that. But there it is a little more complicated in that case to exactly identify. But we figured out more or less how to do it in that case also. So as long as the matrices are invertible, you can invert the matrices. And Smith form is a way to decompose integers, just like you decompose polynomials. Polynomial matrices, you can decompose integer matrices like that. Those things can be used to pre-compute and store. If you know m and n for your build, right? You can pre-compute them, even in the case of matrices. Other than that, we have not seen anything more complicated than that. It has never been a problem.
The autocorrelation is not necessarily a saving in computation, though there is a saving in sampling. Is that correct?
Absolutely. Absolutely. We are not, at this point, we will not have to save. In fact, we don't save because to get autocorrelation within a certain accuracy epsilon, you need about the second number of samples to happen. That doesn't seem to happen. Yeah. What really is that? What really happens is exactly what you said. With a downsampled version, which is especially useful to identify sinusoids from downsampled versions or identify directions from sparse spacing. But one advantage of sparse spacing in physical sensors is that antennas, you space them apart like this, there is mutual coupling. Right? And the mutual coupling problem is always there and adjacent ones especially. Space them apart like that, m can directly be large. So you can make m large enough so mutual coupling is not a problem. And then you can do this kind of yes.
Could this be used more as a sort of test for stationarity or to improve your results in regular sensors by also computing the autocorrelation in this way?
Yes, yes, yeah. The point is that if you have samples, densely spaced samples anyway, right? Then you would probably compute them like that because there is no latency, right? You could use them as a double check, but then either you could use them as a double check, or you could take these results and average those results to reduce the variance of this. You could use them that way also. Yeah. But primarily, the point is that if you have all samples available anyway, then you can save this latency headache and that. So that was not the motivation. That was not exactly the motivation, but you could. Yes.
In the temporal domain, aren't you trading off sampling rate versus the amount of time it takes?
Exactly. Latency. That's what we were discussing.
Right. And how about in the spatial domain? If you get sparse, you also create rate reducers.
Exactly. You create grading lobes. That's a very good point. So the way it works is that grading lobes are especially annoying if this works in a so-called active setting. The difference is this. In an active setting, there is a transmitter and a receiver. Okay? They are co-prime to each other. There, the receiver of the clutter and the target will see both the transmitter and the receiver. Whereas the jammer will see only the receiver. as the jammer is concerned, there is indeed grading rules. Whereas as far as pattern and target is concerned, right? Therefore, it's recommended therefore that this be used in a passive setting. Passive setting basically means there is no transmitter and receiver, there are two receivers now. And then you take the output of the two receivers, compute those averages I mentioned. As long as there is enough leisure to compute those averages, either enough number of snapshots or enough repetitions in the line. So one way or another, if there is enough averaging possible, then it will work, surely. Then there is no problem of grading. But each array individually produces a lot of grading blocks. Yes. Yes.
The relative size of these program numbers does it affect the stability of the distribution?
The relative number so far affects the latency. Latency is clearly stability, the robustness and the stability. It actually does not, because where it matters, not only robustness, because the goal is to compute autocorrelations. Autocorrelation is computed by averaging time snapshots, right? So as long as there is no stationarity, only the size goes up. So as long as stationarity lasts, right, then the autocorrelation will be computed equally, right? Stability in terms of is not there because once the autocorrelation is computed accurately, the rest of the algorithm, whatever the algorithm is that uses the autocorrelation like using and so forth, they will work the same. But another question, very related question that might be of interest, I don't know the answer yet, is jitter. For example, I say, these are the locations. If the locations are not exactly that, but between here and there, that will affect the results in a certain way, right?
But here you assume that
Yes.
system is not covered by noise.
Exactly. Either noise or timing jitter. Yeah. So timing jitter. So timing jitter sensitivity might depend on M and N. And intuitively, it seems that if M and N are large, timing jitter may be more severe. So it's not so clear. But because, see, each separately you sample very sparse. Samples are spaced apart so much, And yet you are trying to create very closely spaced samples, right? So if those samples are spaced with slight inaccuracy, then the different square there, it won't be uniformly spaced anymore, right? Therefore, indeed, those locations that you are able to recompute with the query will be affected by the sampling jitter. That might depend on them. That's a really good question.
Yeah, as you know, the CADX recorder here says that if you sample, you only have a stable sampling set up to, if you were paleo bound with 1, you only have a bound stable sampling set up to a quarter. And if you compound with the symmetric differences,
Yes.
you can get to that unstable sampling set.
Yes.
So is there a process that you recalibrate the system and restabilize the system?
Yes, you can do that. The point is if there is not enough stationarity, you may have to start again. I mean, what I mean is, you do a certain estimate, right? Once you know that the stationarity assumption is not true, you start from scratch and doing the estimate until you again know stationarity is violated. So it is like reinitializing the entire process. Otherwise, it will accumulate.
You reach the, I guess that would be a sort of a bound that you,
Yes.
you could compute ahead of time.
Yes.
Because the CADX theorem is sharp.
Yes. Yeah, but you need to know something about how far the stationarity is valid. I mean, you should know more or less for this duration the signal. Typically from applications, speech, for example, typically stationary for about 20 milliseconds and so forth, right? Once you have that idea, you can work backwards from there. Yeah. Very good.
So maybe if we were to extending this to 2-dimension, I know you covered that.
Right.
Then the idea is you will require the 2-dimension something that is to be co-prime.
Okay, yeah, exactly.
And then you can get a much denser
Can get much
measurement.
Allow me to show one slide on that. Okay? I'm not doing another talking today, but yes, I wanted to answer that question by showing one slide because I'm proud of this. Now, skipping the outline for the second talk. So sensors on lattice. Okay. Sensors on lattice. So these two are open. What that means is a lattice is generated by a matrix. Okay. I am using integer matrices to generate integer lattices. Those two generating matrices are coprime. M matrix and N matrix. Coprime means there is a left common divisor, left common integer divisor is modular. That's what it is. And these are the two lattices. And I am showing that these are sparse by just showing the integer grid. Integer grid means all those things are integers. All those things are two-dimensional. So these are sparse. The claim is that as long as those two are generated by coprime matrices, it can be shown that if you take the difference set, covariance set, it will have all those integers like shown. See those integers you see here? That grid is the same as this grid. If we generate these two sparse matrices using coprime integer matrices, any integer matrices which do not have any left common divisors other than embodiment matrices. If you do so, then the difference square will have all of these, meaning you can calculate the autocorrelation of a two-dimensional weights and stationary waveform at all integrals, no matter how sparse this one is. Exactly same thing, but these are more difficult to prove in 2 dimensions. Proof is not so simple. Intuitively, ideas are similar, but a lot of proofs are. For example, these two lattice generators should be commuting. M times n should be equal to n times n. Because matrices in general don't commute. In this case, if they don't commute, none of the theorems will go through. So that's a mathematical detail, but the point I'm making is that the math in 2 dimension is not obvious. Many results that I intuitively take more work to actually do. Yes, what is it?
Thank you so much, Ms. St.